afternoon, everybody. As you know, my name is Max Aguirre. I'm a graduate student at LSU. I came here to talk about my research, which is related to the development of self-healing and rejuvenator mechanisms for asphalt mixtures containing recycled materials. So as we know, asphalt pavement roads are the most common type of paved roads here in the United States, which means that there is a huge demand for energy every time a new pavement is built. And because these construction materials are so popular, the price is always increasing. So researchers have emerged with these sustainable pavement technologies to address these problems, which is basically to incorporate recycled materials such as wrap and rust, and also we can perform water mix asphalt mixing process. The benefits of using these sustainable pavement technologies is basically we can reduce virgin material consumption, the cost, and also decrease the negative environmental aspect, which is related to building a new asphalt pavement. However, as we know, the main problem of using this recycled material is the age factor, which increases the cracking susceptibility of the mixtures because of the reduction in the capacity of relaxation of the binder. However, we have found rejuvenator products to address these issues. And using this type of products is not new. We usually use it as a surface treatment or we incorporate them into the mixing process. So we were trying to find a new way to incorporate these products. And this is where the self-healing concept emerged. So we are basically trying to mimic the self-healing ability of the skin into asphalt pavements. How can we accomplish that? We have developed two different types of self-healing mechanisms. We have microcapsules containing a rejuvenator product as a core material, and lastly, we have developed these polymer fibers containing a rejuvenator product. So the idea is to incorporate this type of material whenever we are producing a new HMA mixer, and after some years of service life, when a crack starts to propagate, we're expecting the crack to pass through these microcapsules or fibers, break these fibers or capsules, release the rejuvenator product. This rejuvenator product is going to help to dissolve the binder around the crack so we can close the crack and hopefully extend the service life of the pavement. I'm going to focus on polymer fibers for this presentation, as we observed that whenever we were adding microcapsules, we were having a stiffness reduction. So we are not going to have this problem with polymer fibers. The polymer that we chose was sodium alginate. We chose this polymer because of the property, because it is biodegradable. So it's going to give us another way to release the rejuvenator product after some years of service. And basically we're expecting a 2-in-1 product with these polymer fibers. We're expecting some enhancements in the performance of the HMA mixtures, and also we can rejuvenate the binder. The objectives of this project was basically to evaluate the effects of adding these sodium alginate fibers into different asphalt binder blends and asphalt mixtures. So we divide the project into different phases. Phase 1 was basically study the rheological properties of the binder blends, and phase 2 was to evaluate the performance at high and intermediate temperatures of HMA mixture containing these fibers, and also we study the self-healing properties of the fibers. The rheological property of the binder blends were characterized using by performing a PG grading and a MSCR test results. The performance of the asphalt mixtures, we used the Hamburg wheel tracking device test for the high temperature performance and the semicircular bending test for the fracture resistance. And for the self-healing ability, we use a 3-point bending test, which I'm going to explain later. So for the binder blends evaluation, basically we use rotational viscometer, dynamic shear rheometer, and bending beam rheometer. For HMA performance evaluation, we use a semicircular bending test to measure the fracture resistance of the different mixtures. So basically we use a strain control test, 0.5 millimeters per minute at 25 degrees Celsius. And we are getting the JC value, or critical strength energy release rate, from these tests to evaluate the fracture resistance. For the rotting susceptibility, we performed the Hamburg wheel tracking devices. We submerged the specimens on water at 50 degrees Celsius, and the test was completed was stopped after 20,000 passes of the steel wheel. And lastly, we have the three-point bending test setup that we use for the self-healing test. This table shows the experimental test matrix that I used for this project. We have 5 different mixtures or blends. We use a PG70-22. We incorporate 5% RAS, 5% RAS plus 5% fibers. We also use 20% RAP and 20% RAP plus 5% fibers. For the results for phase 1, first we're going to give a quick overview of how we prepare the fibers. Basically, we use a wet spinning process. The setup that we use looks kind of something like that. It's really simple to make, and it is really cost effective too. As I mentioned before, the shell material we use sodium alginate because of its biodegradability properties. And the type of rejuvenator that we are encapsulating is a commercial product called Rejuvenating. So that's a scanning electron microscope image of the fibers. And we also perform a thermogravimetric analysis and some tensile tests in order to make sure the fibers were not going to get destroyed during the mixing process. So for the PG grading results, as we were expecting whenever we were adding recycled materials, the high temperature of the PG grading increased from 70 to 76 with the RAS, from 70 to 82 with the RAP. And also we observed that the addition of these fibers didn't have any effect on the PG grading, or neither on the UTI. For the MSCR test, we observed that the addition of recycled materials and fibers enhanced the performance against permanent deformation as the non-recoverable recompliance decreased, and also the percentage recovery increased as we were adding these recycled materials and the fibers. For phase 2, for the Hamburg wheel tracking devices, we observed the same behavior as MSCR test, where whenever we were adding recycled materials, 5% RAS, the RAS depth decreased. And whenever we add 5% fibers in the mixer with RAS, the RAS depth performance was basically the same. However, whenever we add the fibers in RAP, in the mixer with 20% RAP, the RAP depth increased, and we were not expecting that, to be honest. However, it still performed better than the virgin mixer. For the semicircular bending test, we observed that whenever we add RAS, the JC value decreased from 0.64 to 0.45. However, when we add 5% fibers in the mixer with 5% RAS, it increased to 0.55, so we recovered some performance there. However, again, whenever we add the fibers in the mixer containing 20% RAP, we had a decrease in performance, but still above the threshold level, which is 0.5. Now I'm going to explain the self-healing test. So basically, we are performing a three-point bending test in rectangular specimens. The size of the specimen is 4 by 4 by 16 centimeters, and we use a strain control load of 0.5 millimeters per minute. And the idea is to perform these three-point bending tests to induce a crack on the bottom of the specimen, and we're going to put some specimens at room temperature, some specimens at high temperature, and we're going to be measuring the crack width every day for 6 days using a light microscope, and we're going to measure the crack width every day using a software image analysis. And that's how we're going to quantify the healing efficiency of these fibers. And also we can obtain the fracture energy whenever we were doing the 3-point bending test. So here are some pictures of the results for the room temperature analysis. So this was the control, the virgin mixture. This is the mixture containing 5% rust, 5% rust plus 5% rust. And as you can see, the crack width gets really small just in 6 days. And the last one is 20% rust plus 5% fibers. For the crack width healing efficiency at room temperature, we observed that the mixture containing 5% rust plus 5% fibers had the highest healing efficiency based on the crack width analysis. However, that particular mixture didn't recover that much strength based on the fracture energy analysis. And we have the same pictures for the high temperature environment, and you can also see 5% fibers plus 5% rust. The crack width gets really small again, and also with the wrap, you can see a reduction on the size of the crack. And for this particular healing environment, the mixture containing 5% rust plus 1% fibers had the highest healing efficiency based on the crack width, and it also have a good recovery on strength based on the energy release analysis. So in conclusions, we observed that adding a recycled material increased the high temperature performance rate of the binder blend, and that the sodium alginate fibers didn't have any effect on the PG grading. MSCR test results show an improvement when we are adding recycled materials and fibers in the permanent deformation performance. The SCB test results show that whenever we were adding sodium alginate fibers in the mixture containing 5% rust, we recover some fracture resistant performance that we lose by adding these rust. And for the handwork wheel tracking device test, we observed the same behavior as the MSCR test results, where adding recycled materials and the fibers improve the performance against permanent deformation. For the self-healing test, we observed that at room temperature, the mixture containing 5% rust and 5% fibers got the highest healing efficiency. However, it didn't have a significant strength recovery. And for the high temperature environment, the mixture containing 5% rust and 1% fibers had the highest healing efficiency. Thank you.